Hello. So in this lecture, we're going to talk about neural networks and the backpropagation algorithm. So in the previous lecture, we introduced the idea behind a perceptron and how that was the simplest representation of a neuron. So to take it a step further, we're going to be building a network of perceptrons, which we're going to end up calling a neural network. And one thing that we had said was the limitation of perceptron was that it only worked when we're dealing with linearly separable data. So we showed an example here of the linearly separable data where a perceptron would be able to create a decision boundary, but when we're dealing with non-linearly separable data, then that might pose a problem. Well, unless of course we start doing a bit of feature manipulation. Yeah. But having said that, let's actually get started with the topic for today. So when we're thinking of neural networks, the first thing that comes to mind is, okay, let me actually draw it first. We have x1, which is our feature, x2, another feature, right? And then this goes into our first neuron, and this goes to our second neuron, and here we have our final neuron. So this is an example of a neural network, right? So what we have here is, we call this the input layer, right? So let me do this. No, that's better. We call this the input layer. We call this the hidden layer. And we call this our output layer. So that is essentially how we define a neural network. So we have our input features, right? And these input features, they have weights that correspond to them. So we can think of this as our weights. Let's say this is, let me write it with a different color. So let's say this is our W1, this is our W2 that's going into here, and this is W3, this is W4, right? So W3 going here, W4 going here, and then this is W5 and W6, right? So as you can imagine, when we were dealing with a perceptron, let me go back to that example. So we had this, let's say, we had these three features of ours, x1, x2, and x3, and they had their corresponding weights that were going into a neuron, and then they were generating an output. But now when we're dealing with neural networks, what we have is a network of neurons, or a network of perceptrons in this case, whereby we have this features x1 and x2 going into this layer, x1 and x2, they also they go into this neuron, and then we can build it with as many hidden layers as we want and as many neurons per hidden layer. So that's one thing to note here. So we can have as many hidden layers as we want and as many neurons per hidden layer, right? Of course, the constraint here would be like our computing resources, right? So there's gonna be a limitation based on what our compute resources are, but we're gonna go into that in a future lecture. So this is a simple neural network, right? And we have here a hidden layer. So what we would expect, so let me actually represent this here. By using this. There's a particular reason I'm doing this, which I'll tell you in a moment. So what we have here is, okay, we have x1 times w1, x2 times w2, right? Like we had in our perceptron, and that gives us z1, right? So I'm going to write the z1 in here. So what color should I use for this? Yeah, let's just use the blue color. This is our z1. So we can say z1 is equal to w1 x1 plus w2 x2 plus some bias term, right? So we can have a bias here, which I'll just call B. And if you're wondering what that bias is, the bias is the same thing we had in our perceptron here. When we say W0 is minus theta here was essentially our bias, our W0. So yeah, I'm just using B, but it's essentially the same thing. You can just think of this B as just W0 in this case. I'm not going to go into the reasons why we need that, but like I said in the previous lecture, I do discuss about it in my Bayesian machine learning lecture, so you can take a look at that. So, okay, this is what Z1 is, and then Z2 we can compute in the same way, right? And then we have another item here that I'm going to call A1 and A2, right? So let me just write Z2 for completion, which is W3 x1 plus W4 x2 plus some bias B. Okay. Now we have A1 and we have A2. So if you remember in the previous lecture, I introduced the idea behind the sigmoid function, which is an activation function, right? But I'm not going to, actually no, let me say this. So for us to actually compute this, right, we need to use, in the previous lecture, I just introduced the graphical representation of what it looks like, but the function for the sigmoid is this, which is 1 over 1 plus e to the negative x. And we were using it before to, let's say, compute the probability of an item belonging to a certain class. Like if it's greater than, if W transpose X is greater than 0, then we can just say it belongs to class 1, otherwise it belongs to class minus 1. That's what we had said, if we're using it as a thresholding function, that is. But in this case, we are given the sigmoid function as an activation function, so that we are able to have nonlinear operations on our neuron, right? And we're going to discuss the importance of this later on. But what you need to know here is that after we compute Z1, which is W1 x1 plus W2 x2 plus B, and then we apply the sigmoid function, which is an activation function, right? So that is what will give us A1 in this case, right? So we can say, let me write in the corresponding color, we can say A1 is equals to F, here we've got F of X, right? But it's F of Z1, right? So F of this one, and this is equal to 1 over 1 plus e to the minus Z1, right? That's how we make the computation here for what you call this, A1 over here. So what's happening? So the first thing that happens is we are given two features, x1 and x2, right? We multiply them by their corresponding weights, w1 and w2, and we have the expression w1 x1 plus w2 x2 plus b, and this gives us z1, right? And we take this z1, we feed it in to the sigmoid function, right, to add this nonlinearity, and we end up with 1 over 1 plus e to the minus z1, which is equal to a1. So that's the output. So now we are here, right? So our features have gone through this neuron, right? And the same process is going to happen through this neuron. So we're going to have A1 and A2, right? So A2 will be computed in a similar way, right? So it should be obvious, but just for completion's sake, f of z2, 1 over 1 plus e to the minus z2, and so on. So that's the idea behind this. So we have A1, we have A2, and the next thing is here, we're going to have Z3, right, and A3. So how are we going to compute Z3? We're going to compute it in a similar way. Let me just add this here. Oh, wait. I should write A3 in this color for consistency. So to compute Z3, we will say it's equal to the output of here, which is A1, times W5, plus the output of here, which is A2, times W6, plus some bias. That's what will give us Z3, right? So again, there is another like bias term here, B, but again, not that important right now. Okay, so that is what gives us Z3, right? And then after that, we get our A3, right? We'll get our A3, which, by the way, in this case is equal to, okay, it's equal to f of Z3, essentially. And it's equal to y bar, right? And it's equals to 1 over 1 plus e to the minus, where is it? Z3, right? So that means we can just say, actually, what we need to focus on is this part here, right? That y bar, which is equal to A3, is 1 over 1 plus e to the minus Z3. So why am I calling it y bar now? Because this is the output of this is our prediction, right? So this is actually the output of this is our predicted value, right? And here we're calling it A3, we're also calling it y bar, just to stay consistent with what we were doing before when we're dealing with our perceptrons. So that's the forward pass. You multiply by this weight, you get your Z1. You apply the activation function, the sigmoid function here, and you get A1. And then you multiply by W5 and W6, you get Z3. And you have your activation function again, A3. And then you get A3, which is essentially our predicted value, right? So we have our predicted value y bar, which is this. And that's fine, right? So we call this the series of steps that we're making here. Let me use a different color here. This whole series of steps in this direction. This is our forward pass. Right, that's how we make a forward pass. So given that this is how we make a forward pass, we have our predicted values. But like we said before, when we're dealing with perceptrons, initially our W's, our weight values are random. But what we want to do is we want to essentially correct the values of this so that our predictions are more accurate, right? And to do that, we said we define a loss function, right? And the loss function, we said we're given, let's say, LW with respect to W, right? That's what we defined it here. Like LW, an example loss function was y minus y bar squared or whatever. So let's actually use this. So we can actually think of our loss function as our error term. So let's just call it E. Let's say y minus y bar squared or whatever. This is just an example loss function which works for a regression problem. For a classification problem, we might want to use a binary cross entropy loss function, but we don't need to worry about that now. So okay, this is the problem we have. So what did we say we needed to do in order to actually compute, in order to correct these weight values, right? So that they properly, we update them properly so that they minimize the loss function. So the first thing we said was we need to take the derivative with respect to w, right? Like if you remember in our previous lecture, we said we're given w here, right? We take the derivative of this loss function with respect to w, and then we update it by saying, well, our original weight minus the derivative. So we're moving in a direction opposite the gradient. So we already talked about how we do that in that simple case, but let's look at a particular value of w. Let's say we want to update this one, w5, right? That's the first value we want to update. How do we update it? So we take the partial derivative, right? Let's say of the error term here, with respect to w5. This is what we said. We take the partial derivative with respect to w5. And how do we go about doing that? Well, if we look at the error term, right now it does not have an expression in w5, right? So what we can say is this is equal to the derivative with respect to y bar times the derivative of y bar with respect to z1, right? And why is it that we can say that? Sorry, not z1, it's z3 in this case. Because we've got y bar is equals to 1 over 1 plus e to the minus z3 here. So we have this expression here, which means we can take this derivative, right? So this one we can take it because of, what do you call this? We've got an expression in e and y bar, and we've got an expression in y bar and z3, and then times the partial derivative of z3 with respect to w5, right? Because we have an expression between z3 and w5. We said z3 is equal to a1 w5 plus a2 w6 plus b, right? So we have an expression in here, we have an expression in this term, we have an expression in this term. So we multiply these partial derivatives, and then we get the derivative of the error with respect to w5, right? But we are trying to minimize this error. So essentially we say w5 is equal to w5 minus alpha times the partial derivative of the error, which we computed here, with respect to w5, right? So the same way when we were dealing with our simple case here, or where we just had like 1 neuron, right? We were just saying that w is equal to w minus alpha times the gradient. We are just applying the same logic here, where you say w5 is equal to w5 minus alpha times the gradient, and then this allows us to do our update here. Okay. So again, we are sort of propagating the errors back. This is why this algorithm is known as backpropagation, because we're propagating the errors back. So let's actually go to how we would update w1, right? Because this one might seem like a bit more complicated, but it's not, right? So we started with how we update w5. Next we do w1. And essentially what we do is we compute the partial derivative with respect to w1, right? That's essentially what we want to do. The same thing we did for w5. And this is equal to, so we look here, we have an expression in, what you call this? Okay, let me first write this. Derivative of the error with respect to a1, right? Because w1 is here, so we can have the expression in a1. Right, Even though we don't actually have a direct expression, we're going to infer it later on. Just give it a second. And then we have times the derivative of a1 with respect to z1 times the partial derivative of z1 with respect to w1. So do we have an expression for z1 and w1? Yes, we do. z1 is equal to w1 x1 and so on. So we have this expression. We can take this partial derivative. So this part is okay. And then a1 and z1, do we have an expression for this? Yes, a1 is equal to 1 over 1 plus e minus z1. So we can take the partial derivative with respect to z1 here. And the derivative between e and a1, do we have an expression between e and a1? No, we don't. Right? So what we do is we subdivide this further and say partial derivative of e with respect to a1. And we say this is equal to the partial derivative of e with respect to z3 times partial derivative of z3 with respect to a1. Do we have an expression between z3 and a1? Yes, we do. z3 is a1, w5, and so on. So this part is okay. Do we have an expression in e and z3? The e is with y bar, so we don't. So again, we subdivide this and say the dE with respect to z3 is equal to the partial derivative of e with respect to y bar times the partial derivative of y bar with respect to z3, right? Do we have an expression in y bar and z3? So y bar is equals to 1 over 1 plus e minus z3. So that's fine. This part is fine. Do we have an expression between e and y bar? E is equals to y. Yes, we do. So this is fine, right? And of course, if it wasn't clear from before, the reason why all of this work is because if we cancel these terms, we'll end up with e over w1, right? So if we cancel this and this, we end up with e over w1, and the same goes here. If we cancel this, we end up with that. If we cancel that, we end up with that. So essentially, by breaking it down like this, we can end up computing the partial derivative of e with respect to z3, and then e with respect to a1, and e with respect to w1. And then we can update our w1 has been equal to w1 minus alpha times the partial derivative of the error with respect to w1. And that's how we update our w1. So as you can see, this is how we can update w5, we can update w1, and so on. So this already, this is just to prepare you for what's to come, but this already comes with its own set of problems. The more layers we have and the more neurons we have when we're building these networks, right? And we start having problems that are called like exploding gradients, vanishing gradients, and so on. And we're going to look at all those problems in future lectures and how we can actually deal with them. But as an introduction as to how you can build a neural network, of course, we're building on top of our perception lecture from the previous video. And we say, okay, when we're trying to build a simple neural network and see how the feed-forward mechanism works and how the backpropagation mechanism works, we have a general overview of how we can actually do that. So having said that, I'm actually going to end this here. And in the next lecture, we're actually going to use the PyTorch library to build a simple neural network for the problem where we're trying to predict whether a given tumor is malignant or benign that I showed before. So it's a very simple binary classification problem. We're going to use, I'll show it in the next lecture, the dataset we're going to use, and how we can use a very simple neural network with very simple activation functions, a loss function, and after that, we would have had both the theory and a bit of hands-on practice on how we can actually deal with these networks. So having said that, I'm going to end this lecture here. So see you next time.